Hello class, this is Ms. Riggins with today's video on sections 8.2 sinusoidal functions and their graphs. As you're watching the video, please remember to write down important notes, equations, statements, formulas, or graphs, as well as feel free to pause, rewind, or replay the video as often as you need to get a full understanding. At the conclusion of watching the video, write down a brief summary of what occurred in the video in your notes and submit that summary as well as a top question via the online list the day before class. All right, let's begin. Today we're going to go back to graphs of periodic functions, and we're going to look at a specific group of periodic functions, which are called sinusoidal functions. And the reason why they're called sinusoidal functions is that they look very much like the sine graph. So there are only really two types of sinusoidal functions, sine functions and cosine functions. And if you notice, the sine functions and the cosine functions look very much similar, except it seems like one is the shifting horizontally of the other. And so we're going to look at some other parameter changes and how they affect the graph. So every sinusoidal function looks like either this, where a, b, h, and k are constant values that affect how the graph looks. And in this case, we can deal with only sine or we can incorporate cosine. But either of those works in this situation. There's more than one way to represent a sinusoidal function. You can represent it as a sine transformation, or you can represent it as a cosine transformation. So let's begin. So we're going to look at what each of these parameter changes, how they affect the graph when we change those parameters. So let's take a look at our Inspire. I've created a graph file. I've created sliders by going to Menu, and under Actions at the very bottom it says Insert Sliders. And so our sliders are for A, B, H, and K that we saw previously. And so I'm going to first change A. Right now A is 1. Let's see what happens when I change A. And for the graph, it seems like the graph is being vertically stretched when A is greater than 1, and when A is less than 1, seems like it's being vertically compressed. And that's an example of the transformation that A produces when we multiply the function by A. That's very similar to your project, so you guys already know what's going to happen. But what does that mean in terms of our sinusoidal function? Well, if you recall, A represents the amplitude of the graph, and so when we change the value of A, we change the amplitude of the graph. Now let's see what happens when we change K. When we change K, and I think you guys already know what's going to happen right now, is 0, but if I increase it to 2, it seems like the graph is not changing its shape, it's just changing its position by being translated vertically up or down. Up if K is positive, down if K is negative or gets smaller. And so that's going to affect in our sinusoidal graph not just the position of the graph, but it's also going to affect where the midline of the graph is. And so in summary, in this case, if I have this equation that looks something like this, I can tell you right off the bat without looking at the graph that the amplitude is going to be whatever positive value A is. And then the midline is going to be at y equals k, where k represents that vertical shift. Now, some of you may be saying, what happens if A is negative? Well, if A is negative from our transformation activity, you know that it's going to reflect the graph across the x-axis. But we're going to look for right now when A is positive, and as you can see, that represents the amplitude. When A is negative, the absolute value of that represents the amplitude of our function. So without even graphing the function, I can look at the A value and the K value and tell you the amplitude and the equation for the midline. Now let's take a look at a horizontal shift. How do I affect the horizontal shift? And if you recall, the horizontal shift is going to be labeled by H for horizontal. And I'm going to go in here and I'm going to change. If you remember, to shift something horizontally, we need to change the input. So we're going to do minus H, and that's going to affect the input. And as you can see here, well, you might not have saw because it was so quick. So let me put the amplitude back to 1. Let me put the vertical shift back to 0, actually. And now here we take a look at H. And as you can see, if I move H to 0, it looks like the regular sine graph. But when I change H to a more positive value, it looks like the graph is not changing shape, but is moving position to the right when h is positive or gets bigger, and when h gets smaller, it's moving it to the left. Okay, so that change, but remember, it's important to know that we're talking about x minus h. So where h is a positive number, the graph is going to be moving to the right. When h is negative, the graph is going to be moving to the left. That many units. And that again is consistent with what we did and we saw in our project for the midweek. Okay. Now, last but not least, we're going to take a look at what B does and how B affects the graph. And how B affects the graph is well, we're going to see right now. I'm not going to give it all away. So I'm going to move everything back to regular. I'm going to go in here, and here's my B value. And I'm going to multiply B. Now, it's important that you know that we have to put a parenthesis around x minus h when we multiply by B. Oops, where's my graph go? Hold on a second. Okay, so here it goes. It looks like this. I had typed it in incorrectly. This is the correct expression. When I press enter, it's still not working. Wow. Sorry, I had to put a multiplication symbol in between B and x. Okay, so right now we're not going to be changing a, h, or k. We're just going to be changing B. And as you can see here, B has already changed not the location of the graph, but more so the period of the graph. So here it is normally, but then as I increase B greater than 1, it seems like the period of the graph is getting smaller. So that's going to be a horizontal compression. And when I make B between 0 and 1, it seems like the period of the graph is getting bigger, which is going to be leading to a horizontal stretching. Okay, and it all depends on what B is. So B affects the period of the graph. And I know some of you are saying, well, how does it affect the period of the graph? And we're going to look at that activity in the GEA, but for right now, we're going to look at how it affects it. So the function B affects it by changing the period. So now the period, when B is bigger, the period is going to be smaller, and when P is small, the period is going to be bigger. So there's some type of inverse relationship going on, and this is the inverse relationship here. So the period is going to be defined as 2 pi divided by the absolute value of B. So when B is 1, the period of the graph is 2 pi. When B is 2, the period of the graph is pi, which means it's a vertical compression going from, horizontal compression going from 2 pi to pi every time. Okay. I do want to talk about the frequency. It talks about the number of cycles in 1 unit of time is called the frequency. Now, this is a phrase not that we'll use a lot in math, but you will use a lot in physics when you get there. And the frequency is how many cycles in 1 unit of time does the graph repeat itself. So, or are there how many, and that's 1 over the period, which is an inverse relationship. And we'll take a look at that later on in the activity for the GEA. So now let's take a look back at our Ferris wheel problem, and let's see if we can represent that analytically based off the information that we have. So if you remember our Ferris wheel problem when we first started trigonometry, we need to determine if we're going to use sine or cosine. Then we can determine the amplitude, midline, horizontal shift, or period. So to make life easier, we're just going to go ahead and use sine. So I'm going to say sine. The amplitude, we all know from previous, was 225, the average of the lowest and the highest point. The midline, which we know also, sorry, was that y is equal to 225. And the horizontal shift can be told is because the graph moved over, if we can see, 7.5 minutes. And the period was every 30 minutes. So to represent the period as 30 minutes, then that means that our period, sorry. So our period is 30 minutes. So how do we represent that as a graph, an equation? So we're going to do y is equal to, A is 225, and we're going to use sine. Our horizontal shift is 7.5 minutes. And our vertical shift up is 225 because the midline is at y equals 225. Now the period is the most tricky thing because it's 30 minutes, so we need that 2 pi over b is equal to 30 minutes. And so if we set up that relationship, 2 pi over b equals 30 minutes implies that b will equal to pi divided by 15. And if we were to graph that equation, and I would if I had more time, we could put that into our calculator. The table values we get would look something essentially exactly like this. Okay? All right. The next thing, well, the last thing, I'm not going to really go too much in depth because it's really, sorry. Oh, not the next thing. This is just a summary of what we've already talked about. The next thing is talking about this concept called phase shift. And we don't use it as much in math, but they do use it in applied sense. It's related to the horizontal shift. And the phase shift represents the fraction of the period that is shifted over. So it's not just a horizontal shift. Sometimes that doesn't tell us as much. And to be able to understand what the phase shift is, instead of having b parentheses t minus h, B represents the phase shift, and we can just multiply that out to get what the phase shift is. We'll take a look at it in more depth, but it's not something of great importance in pre-calculus, but it will be useful, I guess, when you get to physics. All right, that's it. Have a good day.